Hello guys, I welcome you to the channel Notabene Tech on Tube yet again with another numerical regarding aerospace dynamics fundamentals. I have taken the examples just from the same book which was actually already been discussed in the last video. The topic is fluid statics, and it is about buoyancy force. And normally when the fluids when talk about the fluids, they are in motion, but when there is no motion, the fluid is normally in the paradigm of fluid statics, and this condition is normally being considered by the help of buoyancy force. So the numerical is also about the same one, and it's why we are discussing the buoyancy force. Normally it will help us in understanding some of the other concepts related to the wing, related to the fuselage, obviously when it's in the buoyancy state. But normally when the air and the surrounding fluid is also helping the aircraft to be in that condition, but we are solely handling the buoyancy force and also the related numerical. The numerical says a hot air balloon with a diameter of 30 feet is carrying a weight which includes the weight of the hot air. A 30 feet is carrying a weight of 800 pounds, which include the weight of the hot air inside the balloon. Calculate first its upward acceleration, and B, maximum altitude or altitude it can achieve. Assume that variation of density in the standard atmosphere is given by this, and which is rho is equal to this, where h is the altitude in feet and rho is in slug per square feet. So how we're going to approach it? First for the upward acceleration, later with the maximum altitude. So we're going to discuss with the help of the buoyancy force. At sea level, normally h is equal to 0 and rho is equal to 0.002377, which is slug per feet cube. It also is in cube. So volume of inflated balloon is, and volume of balloon is normally been 4/3 pi r cube. Okay, and when we're going to apply over here, the diameter is 30, taking as a half, that would be 4/3 into 3.14 into 15 of cube. So that would be, just applying it, 15 raised to cube into 3.14 multiply by 4 divided by 3, that would be 14,130 cubic feet is the volume. Okay, and buoyancy force is equal to weight of displaced air, and which is buoyancy force is represented by capital B, and weight of the displaced air is G, rho volume of that balloon. So G is the gravity and V is the volume, which we have already calculated. So buoyancy force would be B is equal to 32.2 is the standard. Rho is given by this form, is 0.002377, and the volume is 14,130. Okay, we can actually put in the units as well, but right now just multiplying the figures and that would be 10815, or you can say it as 2 pounds. That would be the buoyancy force in pounds. Net upward force is equal to Fn, which is buoyancy force minus weight, and according to the second law of Newton, which is equal to ma. And where m is obviously the mass, and when we're going to calculate the mass, it would be force be already been calculated. Okay, and it's the weight is 800. Okay, and just putting it like this, that mass would be you can put it as F is equal to ma, which is equal to W, and it's been given by A by it's been M, you have to take it W by A, and it would be 800 by 32.2, and that would be 24.8 slug. You have to mention the mass, the unit would be slug. So putting it in this, we have taken we have given the mass, we have the acceleration, and now we can find exactly what would be the acceleration if you want to have the acceleration in terms of this buoyancy force. Okay, we have taken for this buoyancy force, the acceleration would be A, and that would be B minus W divided by M. That would be equal to 1082 minus 800 over 24.8, and that would be 11.4 feet per square. Okay, so that is how you're going to calculate the acceleration. Okay, and when we have actually given, that is also the requirement, you have to calculate its upward acceleration. An upward acceleration due to the net upward force, which is created by the buoyancy force, which is normally is equal to B minus W. Okay, that is the net upward force created by the buoyancy force. And first you have to calculate the acceleration, normal acceleration by the second law of Newton, just putting the normal values, and calculating the mass from the second law of equation, and then when you have calculated the mass, you can apply the same equation for the net upward force, obviously, to calculate the upward acceleration. That is why we have to use B minus W, because it is the upward acceleration, not the normal. So it is the upward acceleration. For that reason, it is been using this. extracting the mass from normally and then applying it for the upward acceleration b minus w divided by m, and you can have the 11.4, which is feet per square. Normally it is the unit of the acceleration in this example. And the second is maximum attitude it can achieve. The second example is maximum attitude it can achieve. Assume that variation of density in the standard atmosphere is given by this. Now we have to take the attitude in consideration. In the first example, we have just taken the sea level height where h is equal to 0. Therefore, this part was normally being considered as 0, so 1 minus 0 is 1, so that is why we have just taken that value in our first part. But in the second part, as it is attitude and obviously it is height, so we have to take this portion of density as well for our calculation. So let's see how we're going to do it. So maximum, number B is maximum altitude occurs when B, which is buoyancy force, weight is equal to 800, since B is equal to buoyancy force obviously is equal to this, which is the how we have defined the buoyancy force, which is the weight of the displaced air, and it is G rho of V. Displaced air obviously when we're talking about the balloon, inside the balloon. So when B is W is equal to 800, maximum altitude occurs when B is equal to weight is equal to 800. Okay, and assume balloon volume does not change. Assume balloon volume does not change. So that would be rho into B of GV 800 divided by 32.2, and that would be volume is 14137, and we're going to actually solve it out. That would be 0.00176 slug per feet of cube. So that is the rho, and from the given variation of rho with altitude h, obviously we have to take it the maximum. We're going to calculate the height from the given equation. Rho 0.02377, 1 minus 7 into 10 raised to power minus 6 height into 4.21. From this we're going to calculate the height. The attitude, we have taken the rho from normally the simple the buoyancy force equation. So taking it as an example of 800, which is also maximum attitude, but for the given condition we're going to use this one. And as we know that rho is equal to 0.00176 slug per feet of cube. So 0.00176 0.02377, and 1 into 7 into 10 raised to power 6 height into 4.21. So how are we going to use it? First of all, 1.00176 divided by 0.00237, and that would be 1 minus 7 into 10 raised to power minus 6 of height, and that would be 4.21. And applying them on a separate scale, it will help us to normally figure it out. So that would be obviously cancelling it. multiplying and dividing. And that dividing on whole side 4.21 and 1.4.21, that was cancelled. So the value would be 1 minus 7 into 10 raised to the power 6 of height into is equal to 0.00176 into 0.002377, 1 over 4.21. Okay, so the height would be calculated. How come? You have to take this figure over here and this figure over here. The plus sign is, this would be plus, and that would, when we take over here, would be minus. So 7 into 10 raised to the power minus 6 height, 1 minus 0.00176 divided by 0.02377, 1 into 4.21, and afterwards its height, and height would be 1 into 7 into 10 raised to the power 6, just getting all together, netting it and grouping or clubbing. 1.00176, 0.00377, 1 into 4.21, that. And when we're going to solve it all together, so first solving this part, 0.00176 divided by 0.02377, and 1 divided by 4.21, that. So the answer would be 1 minus 931. So 1 minus 931 would be 1 minus 0.931 is 0.069 into 7 into 10 raised to the power minus 6. So 10 raised to the power 6, obviously 0.069, 0.0000007. 0.069 divided by 0.000, obviously that would be only 5 zeros, 007, and you get the answer like around about this one, 9857 feet. So that is the answer, 9857, or you can club it round about 9857. The difference is normally the same. We can actually we can calculate and we can use it. 9857 is the answer. So this is how you're going to calculate the height. So I hope that we have covered, with the help of this example, the concept of buoyancy, force, and the fluid statics, and with the help of that we calculated the upward acceleration using the equation for the buoyancy force, and we have calculated the maximum altitude that can be achieved with the help of this equation. And for upward acceleration we have to assume at sea level, and for obviously to calculate the attitude, the maximum altitude which can be achieved is with the inflated diameter and with the weight of 800 pound. So that is with this weight and with this diameter, normally we have to calculate the maximum altitude. So it is quite an easy example, but obviously we have to apply ourselves just for the better understanding of some of the other concepts. So buoyancy force as such in detail with the help of the Archimedes principle, needs to be explained in some other video, but right now I'm just actually getting some of the numerical parts to be fixed in, so that obviously we can improve our understanding. So I'm going to complete this video, I'm going to end up, and I'll hope to see you with some other concepts related to the aerodynamics. So till then, thank you very much, take care, and have a nice day.